In this video, I introduce a restricted Boltzmann machine language model. Restricted Boltzmann machine includes one visible layer and one hidden layer. There are only connections between the hidden layer and the visible layer, but no connections among units in the same layer. We use the embedding matrix R to encode one hard vector input into a low-dimensional feature space to reduce the memory requirement and the computation time. The goal of a restricted Boltzmann machine language model is to predict the next word Wn from his history from W1 to Wn-1. To this end, we define energy function E for joint configuration between the visible and hidden units. The conditional probability of the next word Wn is a margin over hidden state. This is the language model we are looking for, where the normalization factor Zc is a margin over Wn. To use the gradient descent method to train the language model, we define loss function on a training dataset D. Also, we have this loss function LD. The gradient of a loss function L with respect to R and W are computed as follows. This gradient is equal to the difference of two terms. The first term is the expectation of this summation over the training dataset. This V sampled from training dataset, and this H sampled from this conditional probability of H. And the second term is the expectation of a summation over the language model. Here, both V and H are sampled from this joint probability of V and H. Markov and Monte Carlo sampling are used to compute the expectation above. For example, to calculate this expectation of the sum over this P. First, this V sampled from a training dataset, and this H is sampled from a conditional probability of H. To calculate this expectation of a summation over this joint distribution, we need to sample both as V and H from the joint probability. To speed up the simulation, Gibbs sampler replaces the joint probability with two full conditional probabilities. First, we condition the history and this H to calculate the conditional probability of this Vn. And then based on this history and this Vn, we calculate the conditional probability of this H. So we got the samples here. And then we substitute these samples in this expectation to calculate the expectation of this sum over this joint distribution. Regularly, for each training sentence, we need to sample Markov chains until reaching the equilibrium distributions. Since restricted Boltzmann machine training only care direction of a gradient in each step, we don't need the sample until convergence for each input sentence. So here we use a contrastive divergence algorithm carries out only one iteration of full conditional distribution to capture the descent direction. For more details, please check with this reference. Thank you.